right, well, here is the answer key for the review for the powers, roots, and radicals assessment that you're going to be taking tomorrow on Wednesday. So just so you know, on the answer key, the one that's printable that I emailed out, my number 9 has a mistake on there, and I'll take care of that mistake as we go through this one. But let's start with number 1. So again, I want you guys to have your cheat sheet, the one at the exponent table, and I also want you to have your flow chart in front of you because those are the tools that I'm going to be using when I go through the review. So starting with number 1, since it's a radical, the first thing my flow chart tells me is to take out anything that's perfect. And looking, I can take the 8 out. 8 has a perfect cubed root, and the cubed root of 8 is 2. I can take out the x cubed, and remember with this, with exponents, I divide the exponents. 3 goes into the 3 of the power perfectly one time. And then 3 goes into 6 perfectly as well, so all of the y can come out 2 times. And then 3 can go into 4 times, into 4 once, so some of the z can come out. But when I do the division, I'm going to have a remainder, and that remainder of 1 is going to tell me how many z's I have left. So still in the cubed root, I still have 1z, and so this would be my answer. And I'm just going to separate the radical from the exponents, but this is number 1. So a lot of the stuff came out perfectly, but not all of the z. All right, looking at number 2. So when I look at my cheat sheet, again, I'm going to see the 16 or 8 have perfect fifth roots. Neither of them do. So I'm going to, according to my flow chart, ignore the fifth roots, multiply 16 and 8, and bring the root back. So when I multiply them, I get 128, and then I look back on my cheat sheet, and 128 doesn't have a perfect root. But if I change the factors, there's a different set of factors that do. So I'm going to break the 128 down into 32 and 4. And now the 32 can come out. The fifth root of 32 is perfect. That's worth a 2. But then that 4 is going to stay in there. So this ends up being my answer for number 2. All right, number 3, whenever I add or subtract with radicals, whenever I add or subtract with anything, things need to be perfect. Because in this problem, I'm going to be describing how many square roots of whatever's in the root that I have. So what I do is I always go to the largest one and I change that first. So 45 doesn't have a perfect square root, but I'm going to break it down into the factors of 9 and 5. And then the 9 can come out and become a 3. And now I'm just going to rewrite the original 5 square root of 5. So when I look at how many square roots of 5 I have 2 of them. And there's number 3. All right, moving on to number 4. Again, I'm still working with radicals, so the first thing I'm going to look in either root is anything perfect, and nothing's perfect in either of the roots. So now, according to my flow chart, I'm going to ignore the fifth roots and take 27 times 9, which is 243, and I'm going to combine my x's. There's a total of 5 of them. And now I'm going to bring the fifth root back, and as it turns out, 243 has a perfect fifth root. It's 3, and then the fifth root of x to the fifth is just x. So there's number 4. Number 5, same thing. I'm going to take out whatever I can that's perfect with my cubed root. So 64 has a perfect cubed root. That can come out and become a 4. X to the fourth isn't perfect, but some of it can come out there. So when I take 3 into 4, 3 goes into 4 one time. But I'm still going to have a remainder of 1x left in there. So there's the x that's left in. And then 3 doesn't go into 2. So all of the y is going to have to stay in there. And then this is my answer. Somebody in second or third hour asked me, do I have to separate the answer as much as you do? No, you don't, but I just want you guys to realize that this cube there belongs to the root and not the exponent. So I just do that so you don't get confused, that's all. All right, let's go to number 6. So number 6 I did do in most of the classes, but let's just go over it. The first thing I'm going to do is take out anything that's perfect. So what's perfect in the numerator is y to the 4th. And what's perfect in the denominator is the 49. And that's all that's perfect. But now what I'm going to do is I notice that in both the numerator and the denominator I have x's. So I'm actually going to simplify my x's. And x to the 5th over x can turn into x to the 4th in the top. And now that x to the fourth is perfect. So the square root of x to the fourth is x squared. So it's joining the other things that are on the outside. Now I'm going to look at the 18. The 18 isn't perfect, but it also has perfect roots or factors that do. So I'm going to take the 18 and I'm going to break it down into 9 and 2. And now the 9 can come out and join everything. So I'm going to squish it in there. And so now when I look what's still left inside a root, I'm going to switch the colors up now, is in the numerator I still have a square root of 2, and in the denominator I still have a square root of z cubed. Now in the denominator I could take some of that z out, but no matter what I'm going to have to rationalize. So I'm actually going to go straight to rationalizing. So at this point what I'm going to do is rewrite what I have on the outside. So I have 3x squared, y squared, 7. And still in a square root, I have square root of 2 and the square root of z cubed. And I'm going to work to rationalize this z cubed. So remember, in this exponent spot, that's like having a 2 there. So I need, so I'm going to actually write a 2 there, for this z to have an exponent that 2 can go into. And 2 can go into all of these numbers perfectly. So when I look at that list, I'm going to pick the first and smallest number after 3, and that's 4. This is how many z's I need. So I have 3 right now. So when I rationalize, I'm going to add 1 more, so I now have 4. So as far as the denominator goes, this part right here, this is now the square root of z to the fourth, and that has a perfect square root. So when I go for my answer, the square root of z to the fourth is z squared. So I'm going to take that z squared and add it to my denominator. So in green, this is my final answer. I had a 7 before, and I'm going to add a z squared. And then as far as the numerator part goes, instead of leaving them separate in square roots, I'm just going to put them together. So there's the 3x squared y squared that was there, and now I'm just putting the 2z into one square root rather than keeping it separate. Okay, so there's number 6. Kind of all over the place, sorry about that. All right, let's go to number 7. So now I'm back into exponents. Again, I told you guys in class, I'm not assessing your knowledge of fractions. So if you want to use a calculator to type in the multiplication or the addition of fractions, go ahead. The first thing when I look at my flowchart for exponent, it says deal with parentheses. And since I have parentheses, this 1/2 is going to distribute to everything in here. Okay? So when I take 25 to the 1/2, I've also talked about that I want you guys to remember that anything to a 1/2, 1/3, 1/4, I want you to automatically think of it as that root number. So that's the same as the square root of 25, which is 5. 1/2 to 10, the a is going to become a to the 5th. And then 1/2 of 16, that's going to become b to the 8th. And that's it for 7. Number 8, same thing, exponents. So the first thing I'm going to deal with are the parentheses. I should multiply my exponents. So when I do that, I get x to the negative 2/3. Then in my flowchart it says organize, move any negative exponents. I do have a negative exponent, so it's just going to move to the top. And that's it for number 8. Number 9, same thing, a little bit bigger than number 7. In most classes we did do this problem. So starting with number 9, the squared is going to go to everything that's in the parentheses. So when it goes to the 3, it becomes 9. When it goes to x to the 1/4, 2 times a fourth is a half. When it goes to the 2/3, 2 times 2/3 is 4/3. And when it goes to the z, it simply becomes z squared. And now it's also going to go to everything in the bottom. So 2 squared is 4. When it goes to the x, it's just going to become x squared. And when it goes to the 1/2, it's just going to become a y. Now in my flowchart, it says organize, move any negative exponents. I don't have any negative exponents, so I'm just going to organize. So first, with the 9/4, I can't simplify 9/4 as a fraction, so I'm just going to leave that as 9/4. So I'm starting to get my final answer. Now I'm going to look at the x's. My job is to subtract the exponents. A half take away 2 is negative 1 1/2. So as a fraction, that's negative 3 halves. And remember, that negative 3 halves is actually starting out on the top, but because it has a negative exponent, it moves to the bottom. And that's the mistake I had on the printable answer key. I left it in the top. With my y's, 4/3 minus 1 is a third, and that's in the top. And the z, there's nothing to combine with, so it just stays up there. So there's number 9. Number 10, going back to my flow chart, this time I'm looking at the radicals. So what's perfect? X squared is perfect. It gets to come out. Then it says if roots are the same, which they are, I'm going to ignore the square roots and just take 12 and divide it by 3, which is 4. And now that has a perfect square root, and that becomes a 2, so it joins the x for 2x. Number 11, the first thing I'm going to look at is anything perfect. So do 5 or 27 or x cubed have any perfect roots? No. I can't simplify 5/27 as a fraction, so the only issue I have to deal with is rationalizing. So what I'm going to do is build up the fifth root, and I need to turn 27 into a number that has a perfect root. And when I look at my cheat sheet, the exponent table, 243 has a perfect fifth root, and if I take 27 times 9, I get that 243. And as for the x's, again, I need 5 to be able to go into a number perfectly, and 5 goes into 5 and 10, 15, etc. perfectly. So when I look at the first and smallest number after 3 in that list, which is 5, this is how many x's I need. I have 3, so I'm just going to add 2 more. Now, as far as the denominator, it ends up becoming the fifth root of 243 and x to the fifth. And both of those have perfect fifth roots. 243's fifth root is 3, and the fifth root of x to the fifth is x. And as far as the numerator goes, when I look here, what I'm going to do is just combine them into one fifth root rather than having them be separate. So I'll multiply the 9 and 5 and bring along the x squared. And that's number 11. And then the last one, number 12. The first thing I'm going to do is look, is anything perfect in each one? The y to the fourth is perfect. That's going to come out. That becomes y squared. In the other square root, the z squared is perfect, so that's going to come out. It's all multiplication, so I'm just going to put it up here. And now, since they are both square roots, what I'm going to do is combine what's left. So I'm going to combine my x's. They become x to the fourth. And I have a y and a z that just join it. And now I'm going to take the x to the fourth out. That can join the other squares and become x squared, y squared, z squared. So when I'm done, here's your final answer. This is everything on the outside, but still inside is a y and a z. And that's number 12. All right, what I'm going to do is stop this one, and I'll do another video answer key for the back page.